So thanks again to Angelo. Next up, we've got Antoine Tilloy. So Antoine, if you can go ahead and share your screen.
Okay, let me try. Does it work?
Yes, I can. And you've got Overleaf open at the same time, like a yeah.
But now you see the slides only?
Yeah. Perfect. Okay. Yeah, we can see the slides. Okay, great. So I'll hand over to you. Thanks so much.
Okay. Thanks a lot for the invitation and this very nice workshop. It's very nice that Angelo talked before me. In a way, it's a nice follow-up. You'll see that I'll try to discuss some aspects that are in a way related to the questions that were asked at the end. The objective of this talk is really quite modest. So what I would like to do is a bit clarify in collapse model what is a quantitative prediction that you can measure in experiments, for example, and what is a useful metaphysical simplification that is brought by these models. Sort of understanding the measurement problem, for example, for me is a metaphysical simplification. I don't mean the second one negatively at all. So to me, it's also something very important about the models, but just try to really distinguish in these models the two aspects. And I would like also to clarify, I think, in what sense, at least current collapse models differ from quantum theory, understood very broadly. So this is inspired from an essay and so that I wrote, and I insist it's an essay in the sense that it doesn't really contain anything new that is unknown to the collapse practitioners. So everything I think is fairly well understood in the community, but yeah, my hope is a bit to try to explain it to the community more broadly. So let me recall the main idea of collapse models. So this can be very easy after the talk of Angelo. The idea is you start from the Schrödinger equation and you had some p-naught nonlinear perturbation, so a very tiny thing that should collapse macroscopic superpositions, but keep microscopic dynamics roughly the same. And like Angelo, I insist that H, so the dynamics you put in is basically the standard dynamics you have. So if you could deal with everything in full generality, you would like to use even the standard model Hamiltonian. In practice, it's very hard to make concrete predictions in this context and even have consistent collapse models in this context. So typically, people use a non-relativistic simplification. So at this stage, this looks somehow ad hoc, and I'm fine with it being ad hoc. So in this talk, you can even imagine like it's like nature is like that. Now to make things concrete, I just present you one collapse model, so the Ghirardi-Rimini-Weber model. So it's a bit different from the CSL model that Angelo presented, but it's in a way the simplest one. You imagine that you have a system of n distinguishable particles, so that's your non-relativistic quantum mechanical model. And you imagine that every dt, you have a certain probability that the case particle collapses around a certain point. Upon collapse, the wave function is multiplied by an envelope around this collapse point. So this is the wave function before collapse, and this is the wave function after collapse. And the probability of collapsing in XF is given by the Brown rule here. So that's the rule. That's the new dynamical law of the model. This is the epsilon part. So this is what you add on top of the Schrödinger equation. Why it works, again, Angelo explained, I think, very well. So this is just to give an idea. If you put the historical values of the parameters, an electron's take, I think, 300 million years to collapse, while a cat with many electrons is actually, I said localized up to RC. That's actually to much less than RC. In less than a picosecond. So macroscopic objects are localized instantly, while microscopic things are almost untouched. And in brief, there are actually, that's I think one of the great achievements of this program. You can sort of semi-rigorously derive the measurement postulate just by studying the stochastic dynamics of measurement devices. So you just have a single dynamical law for the small and the big, and from that you can derive the collapse, the measurement postulate, so including the Born rule and the collapse. And yeah, small stuff doesn't collapse because of its intrinsic dynamics, but small stuff collapses because it's coupled to big stuff. And you understand that just from the equations. Okay, so I think that's a very neat aspect about these models. Now, what does this theory, so this is a more philosophical part, if you like, say about the world? So now you have no measurement postulate anymore, you have stuff that moves. And you have to ask, what is the stuff now? So what is the world made of that is moving? And there you have sort of various prescriptions. You can decide that what is real is, that's the most naive thing, I think, the wave function itself. So you just say that matter, if you like, is the wave function. However, it leads to complications, and sort of there is a long literature of subtleties related to the tail problem that I think there are arguments that you can still avoid it by keeping this prescription, but I think the easiest way is to just commit to a different ontology, to just say that what is real is different. And one option is to take the mass density. So now you have a sort of scalar field in space that is a function of the wave function, and that tells you how much matter there is there, how much stuff there is. And this is what is real and what moves in this model. And if you do that, you can understand measurement from the position of pointers, for example, and that if the pointer is on the left, there is stuff on the left, and if it's on the right, there is stuff on the right. You can also, another option, which I particularly like myself, and that I think is quite minimalist and neat, and you just declare that the only thing that's real are the collapse points. Okay, so these centers, they occur at a certain position, xf, and time tf. And you just say that these events are what's real, they are the flashes. So nature emerges from a sort of pointillist description. Okay, so that's an option that was suggested by Bell, as far as I know. I think this is often considered a bit anecdotal or redundant, or in some circles worse than all that is philosophical. I don't think so. So I think these prescriptions are in a way as metaphysical as the wave function prescription, so as the stochastic dynamical law itself. And I'll try to give an argument for that. And in a way, this talk is a bit, the objective is to clarify that, I hope. Okay, experimental consequences. Angelo gave a lot about this, and I'm a bit ashamed that this is a sort of outdated graph that is from my own paper. So Angelo's graph is much more accurate right now. But the main effects, I mean, you have loss of interferences for big stuff. Matter slowly heats up, stuff vibrates, and photons get spontaneously emitted. And quite unfortunately, at least in my opinion, or sort of, it's purely aesthetic judgment, the interesting or neat effect that is very intuitive, loss of interferences, tends to constrain collapse models much less than side effects, the fact that matter heats up. But I go quickly on this because it's not the core thing. So this is now related really to the question that was asked at the end of Angelo's talk, and that I think is really crucial, is could we have done things completely differently? And as really Steven Weinberg tried to propose a model of modification of quantum mechanics that would be deterministic. But there is a theorem, I should say, it's perhaps more a pseudo theorem by Gizin, a sort of a very strong argument, that nonlinear deterministic modifications of the Schrödinger equation always allow to send signals faster than light, or break the Born rule in a non-trivial way. And the reason is, so I'm just paraphrasing what Angelo said again, is that you have a proper statistical mixture that is, so you consider, an EPR situation where Alice and Bob share an entangled pair, a proper statistical mixture that is Alice measured, but Bob doesn't know the results, or an improper mixture that is the state is still entangled, Alice did not measure, is locally distinguishable by Bob. So if Bob waits long enough for the nonlinear dynamics to modify the mixture, Bob can know if Alice measured or not. And this really all happens locally from the local dynamics. So there is a way to, it's not so much that the collapse model sends information faster than light, rather that it reveals local entanglement in a way that allows to send signals. There are lots of ways to try to make nonlinear models that still preserve, sort of to modify the collapse rules in complicated way to save the phase. But I think at the end of the day, they are super contrived, and yeah, there is a strong case to be made that if you distinguish proper and improper mixtures, even if it's complicated, I will always find a way to exploit it to send signals faster than light, or to break the Born rule in such a way that you can never make predictions about anything. So why are we saved? Because in fact, the modifications we have is nonlinear as well. But the crucial point is that in practice, we only ever measure frequencies. And the whole point of this GRW model is that at the end of the day, you effectively recover the Born rule. So we can still use the Copenhagen formalism to make predictions about experiments. So frequencies we measure are, to simplify, given by expectation values of projectors. But on top of this, you have jumps in the wave functions, and they are not knowable a priori, so only a posteriori. And so the frequencies are given by the expectation values of these frequencies over the randomness of the noise. So here, this is really a statistical expectation value, a statistical average, sorry, of the noise. And if you look at it, you realize that you can take the trace out, take the expectation value of the ket bra of the state, and this, if you write this, if you know this density matrix, you realize that all the falsifiable predictions you can make about the model, I mean, really numbers you can extract from experiments, are contained in this density matrix. And now, of course, the collapse probabilities of GRW, so the link between the envelope, the probability of collapsing, and the probability of collapsing in the certain point, have been chosen exactly in such a way that when you take an expectation value, all the nonlinearity runs away. This is always a bit more difficult to see with the CSL and Yoshi-Penrose model, because there you have to use Ito calculus to see the cancellation. Here, it's really completely obvious. So if you write down this expectation value, you realize instantly that all the nonlinearity is taken away. And you have an equation for rho that is of the Lindblad form. And these are the envelopes, the Gaussian envelopes I mentioned before. Okay, so that's why GRW models, and in fact, all collapse models that have been proposed and studied, evade this problem. But at the end of the day, the thing you use to make predictions is linear, in fact. So you have, for collapse models, I think 3 levels of description. The first is, what do they tell you the world is made of? What is the stuff that moves? And there, okay, you have, for example, the flashes or the mass density. Then you have the empirical contents, that what are the quantitative testable predictions of the theories that you could measure in experiments, and it gives you a number, it's like 2.3, and you can compare with the prediction. There, everything is contained in a master equation for the density matrix. And then you have an intermediary object that is sort of convenient to get an intuition of what's going on, that you can use to get the probabilities or the evolution for the ontology, for what the world is made of. But that doesn't itself has a very clear status. That is, it tells you more than the empirical content, and in a way, it tells you a bit less than what the world is made of. It's an in-between object that has a not so clear status. And yeah, so far, collapse models are all, I think all reasonable collapse models are given by a master equation. So here, to simplify, I wrote a Markovian one, and everything I will say will be about the GRW models, so a Markovian collapse models. But you also expect that the evolution for the density matrix should be linear for non-linear collapse models. Things I say would just be more complicated for these models. So this is the only thing you can probe in an experiment. So maybe as an intermediate step, you will use the wave function, the stochastic wave function, to have a feeling of what you could test in your experiment. But at the end of the day, everything should be computable from an equation of this form on the density matrix that never makes any reference to the noise, okay, or any reference to the classical noise. That's actually a good sanity check to make sure the effect you are looking for is real. Now, if you measure something like that, what does it tell you about the underlying nonlinear model? So can you know from making measurements on this that you are testing the GRW model? And weirdly or surprisingly, or I don't know, maybe it's intuitive, but it tells you actually very little. And this is for two reasons. First, because of the plurality of unravelings. So if you have a certain row verifying an equation of this type, you always have infinitely many stochastic equations for psi, for the stochastic state, such that upon averaging, you get the same density matrix. And another is that because of dilations, you can always find a bigger Hilbert space. So it can be super contrived and ugly and all you like, okay? I'm not saying it's a natural evolution, but you can always find a dilation such that you have a unitary evolution for the bigger state, and that row is obtained from tracing out this. I insist the evolution can really be ugly and violate all the principles we're used to, but still it's unitary Hilbert space. These two things can easily be done for the GRW model. And maybe to give an intuition for, these are usually proved in the continuum, and then it's not always so trivial to understand what's going on. I think it's very easy to understand with, in a discrete time setting, a good way to reproduce the GRW model effectively, or these collapse models, and imagine you have a system of n particles, and periodically, but very fast, in a sort of stroboscopic way, you send many probes that can be two-level system, for example, into the system. They get coupled, and far away, or just say immediately, you measure them. My claim, that I won't prove here, but it's quite easy, is that you can devise a measurement on here that is such that the stochastic evolution for the n particle system becomes that of GRW, or approximately GRW. If you make another measurement on these probes, then the stochastic evolution of the state becomes completely different. You can even make some where cats don't collapse. But you can also decide not to measure the probes, in which case the evolution is fully unitary for the probe plus n particle system, and you get the dilation that I mentioned. The thing that is important is what you do to the probes. They don't interact again ever with the system. In this Markovian case, you can do it in a galaxy far, far away, even 1 million years after. So everything you do after on these probes can have no impact on everything you would ever measure on the system. And that's the way to understand why all these different unravelings that correspond to different measurements on the probes, or no measurement at all, which corresponds to a dilation, give exactly the same predictions on everything you could measure here. And if you do this in a neater way directly in the continuum for the GRW model, you can construct empirically equivalent model, in the sense, not in the sense that they solve the measurement problem, but in the sense that they will give the same frequencies for measurement results that are stochastic but continuous. So this is your GRW model, sort of, you have discrete jumps that create a pop, but you can create a version that is stochastic but continuous and doesn't collapse cats. And you can add a weird deterministic one that is unitary in a larger Hilbert space. So it's sort of like if you added a peculiar, and I insist very peculiar, dark sector in the standard model. So that's the situation for for this model. So I think it's good to have an intuition that you can reproduce with completely different evolutions the same kind of predictions. And this actually is not so intuitive and it seems at first sight that there is a counterexample to this statement I'm just making. And it took me a while actually to understand why it was not a counterexample. And that's a bit that relates to the title of this talk and actually why I wrote this essay in the first place, which is there is an interesting paper by Feldman and Tumulka where they tried to test collapse models by looking at many possible signatures. As there is one that is interesting is sound. So if the collapse parameters were tuned in such a way that the collapse radius was very small, each collapse would make an audible bang. These values are falsified, okay? So these values are falsified by other methods. But now imagine, just for the sake of the argument, that you live in a world where collapses are even more rare in such a way that in a given room, for example, you have only a collapse every 10 seconds or so. But that really the collapse makes an audible bang. Again, this is falsified, but it's to understand what's going on. So every time there is a collapse, there is a bang. It would seem, and this is pretty clear from the standard GRW picture. This is completely understandable from the jump process. But as I told you, the jump process should not be testable directly because what we can test is only raw. And in fact, if you take the two other descriptions, the stochastic one and the unitary one, it would seem that you hear only a constant buzzing with the first one because it's driven by Gaussian noise. Or maybe in the unitary one with a peculiar dark sector that you would just hear no noise at all because it's sort of deterministic in the bigger space. Okay, so there you have to stop for a bit because I think it's really a mathematical statement that in these Markovian collapse models, you can never know the difference between different unravelings. And so here it seems we have an example where it's not the case. And in fact, the story is actually that I think empirically all models will actually agree and that the results from the standard GRW model is the right one. That is, in both cases, we would hear bangs. And this can be understood with the sort of many worldish description of the second situation with the continuous GRW and deterministic models. If you look at the support of the wave function in the configuration space, you have sort of a big branch of the wave function where there is no bang that is really macroscopically different from the one where you heard a bang. And for the other two models, there is no jump. It's more that the weight of the wave function progressively leaks from one branch to the next. And at some point, you have a macroscopic superposition of the two branches. But we know that in practice, in the many world view of it, you sort of, the consciousness of people just goes to one of the branch. Like everything in the world follows. If you have two macroscopically distinguishable branch, you basically are as if there is just one. And this is the sort of naive decoherence account of things. And it's the same reason why, even though there is no fundamental photon jumps in nature, we still see and understand photon clicks from standard QED with a sort of hand wavy decoherence many world argument. So I would like to really summarize the reasoning. Sorry, it's a bit verbose, but I think it's important to summarize the reasoning. And what I'm trying to explain in this talk is that at the beginning, you introduce a nonlinear modification of quantum mechanics to solve the measurement problem. And these modifications, they have experimental consequences, and it's an advantage or an inconvenience depending on your point of view. Okay, I think many people see it as an advantage because now you can probe these experimental consequences. But what you realize is that these modifications are extremely constrained by the need for a linear master equation. Otherwise, you lose everything, all hell breaks loose, okay? You have faster than light signaling, all kinds of problems. And this master equation contains all the predictions, all the quantitative predictions you can make about the model. Of course, they do not contain what I call here the metaphysics, again, not in a negative way, but the fact that it tells us what the world is made of and how we solve the measurement problem and all that stuff. but the issue is then you have infinitely many stochastic models or even unitary ones that can reproduce the same master equations. And thus, they can also reproduce everything we can measure about these models. So in fine, collapse models do solve the measurement problem, but I think their empirical content does not differ so much from quantum theory if you understand it very broadly, because there exist unitary versions, even though they are ugly or weird, that reproduces it, but rather from the standard model, that is a specific instantiation of quantum theory into a precise model with a certain number of particles, laws, and whatever. And then if you ask for certain principles in the standard model that interactions should have a certain form, then you may disallow this weird unitary evolution that would reproduce the predictions of collapse models. Now, I think it brings an interesting question if one day the predictions of GRW or another collapse models are actually verified. So I don't know if that's what we expect. I would say it's probably not what I expect, but what happens if experiments show things that are exactly in agreement with GRW? I think logically, you can still defend an orthodox view of quantum mechanics with a many world or Copenhagen version, just by introducing a sort of peculiar non-relativistic dark sector in the standard model. Of course, I think the GRW account would have had the great advantage of having predicted everything in the first place. And of course, you can say the story with GRW is much more natural. But I'm really wondering what the community would choose. Because we are so, I mean, theoretical physicists will so like to interpret everything in terms of some hidden evolution, even though the GRW account would be appealing, the standard one. I'm not even sure people would not immediately start hunting for a dark sector. And finally, so these are the, so what I think, what I think are the main things I take from the collapse program, and that I think it is great for, is that it's a very good illustration that naive realism, like you just imagine the world is made of stuff that moves, is not only tenable, it's a completely acceptable position, but it's also not crazy contrived. There is also always a kind of view that if you want a simple interpretation from quantum mechanics where you just have stuff there that moves in a fairly reasonable way, it's impossible, or it has to be super contrived. And collapse models are a beautiful illustration that it does not have to be so. Also, it's another illustration of a well-known fact that you don't need collapse models to know, but that metaphysics is always very underdetermined by experiments. So it's really true always, but here it's particularly clear because it's very easy to make other accounts with different unravelings or dilations that give completely different metaphysics and give the same predictions, and that are not completely weird. We are not saying that angels are moving particles, for example. They are just similar accounts. Also, I think they are an excellent starting point for theory building. And so at the end, I think it was, again, a very interesting achievement, even though the talk in a way may appear critical of some aspects. Because I think I remain very, very enthusiastic about the results of this program. So thank you very much. I stop here. I don't know if I ended up too early actually, but
no, that's totally fine. We can. It's good to have time for questions. Thanks very much for that talk. That was really, really fascinating, interesting content. Okay, I can open the floor to questions now. So if anyone has a question, just raise your hand. So, Peter Morgan.
Hi. Oh, I can't start video, so fine. My confusion. Thanks, Antoine. A really nice talk. I think you clarified for me a great deal about GRW. I wonder, though, what attitude you have to take to measurement incompatibility and the violation of Bell inequalities, insofar as those kinds of theorems are demonstrations that one it's useful to use a quantum probability kind of approach in which there is measurement incompatibility, as opposed to using a classical dynamical approach, which would be appropriate for the master equation that you've constructed. So is that clear what I just asked, or shall I restate?
Yeah, so if you want to understand, I think there is no difficulty with collapse models to understand a Bell type situation with violations of Bell inequalities just from stuff moving on each side and the pointers moving one way or another. And then you understand stuff from things from the fact that the global stochastic law of these evolving things has some non-locality in it. So the prescription for the matter, including the stochastic parts, does have some non-locality in it.
Right. Okay. Thanks.
So yeah, that's.
Okay. Any other questions? I might ask one then. So I find all of this super interesting, and I find both the questions of how we can test collapse models and also what story collapse models might be able to tell us very interesting. I mean, collapse models are there to solve ultimately a kind of problem of how we get the emergence of the classical world and tell a consistent philosophical story about what exists. The thing that comes up for me is both this problem in a problem in the consistency of that story, and a problem like you're raising in the sense in which it can be tested. So given what you said about effects of collapse models being on some level intrinsically that they have to be the same as the kind of effects that we can get from decoherence, do you think that it's possible to verify a collapse model in the first place? And just to add into that a little bit, so this is similar to the question which I asked Angelo, and Angelo said that there's a nice way to distinguish between collapse noise and ordinary decoherence noise, and this comes down to the way that you get like a mass resonance in particular models, or there's certain levers which you can pull which will help you distinguish between these two. Does those methods of distinguishing between ordinary noise and collapse noise rely on some level upon the stochastic unraveling? I hope that's not too much of a question.
So the question of a quantum noise is really, in that case, comparing the standard GRW account to the deterministic dilation. I think, at least in these Markovian models, it's always doable. And it's a quite standard construction in quantum optics to do it. So the question is, at a fundamental level, there will always be an existing Schrödinger equation on a bigger Hilbert space that reproduces everything. So it's going to be completely undistinguishable from decoherence. The thing is, and I think that's where Angelo, so it seems to contradict the points of Angelo, what I just say. This unitary evolution does violate things we like from Hamiltonians. So that's why I say it's a bit ugly. For example, typically the Hamiltonians, to really reproduce exactly GRW without approximations, you typically use Hamiltonians that are not bounded below in the dark sector. So they will violate, they typically are not quantum field theory Hamiltonians. They are Hamiltonians we would dislike usually, okay? I unfortunately didn't put these explicitly, the Hamiltonians in, but you can really write them down fully explicitly. So it all depends on what you are willing to call a quantum theory. If quantum theory, it's just a certain Hilbert space, no matter how big, in which you have a Hamiltonian evolution, I think it's forever undistinguishable, the two, empirically. If what you call a quantum theory is the usual laws of quantum mechanics plus some requirements on what is a reasonable Hamiltonian for matter, what is a reasonable particle-like bass, for example, then you can distinguish. So, for example, a reasonable particle bass will typically have cutoff frequencies. that here, artificially, these Hamiltonians have infinitely high frequencies, the one you have to reproduce exactly GRW. So you have to add extra constraints. And what I try to say at the end is, my opinion is that it's never going to be possible from experiments to make to even falsify linearity of quantum mechanics in that sense, linearity at the wave function level. It's always going to be what is the best account of what you have seen. So you're going to have two stories, and you have to see which one is. You have to use some other argument than pure logic. There's something like Occam's razor, or to say one account is the best. But I think logically you can always make these two accounts, one GRW and a sort of contrived but fully unitary one. And I think in the collapse community, it's sort of, or even in the foundation, sort of obvious that we would choose the GRW account because they predicted it, and it's sort of neat, and it solves the measurement problem. So it does a lot of things for us that the unitary account doesn't. But I think the attachment to the unitary story is also so big in general in the physics community taken more broadly, that I'm not even sure people would choose the collapse view. So it might be that even if it's verified, people will immediately start, making sure, is this trying to probe the properties of this non-relativistic dark sector. If GRW is true, there will sort of be nothing to probe more than what the GRW master equation says, because this is, again, a peculiar dark sector that doesn't send information back. There's just think of information, but there will always be these two competing stories.
Pavel?
I have to mute. Thank you very much for fantastic talk. I would like to ask one question, because first, well, actually two. First, do I understand correctly that you say that the collapse may never be falsifiable in a strict sense? This is a quick question and probably a quick answer. The second is it possible that there is some Occam razor for those dilations, in the sense that the unitary theories that would come out, they somehow are not compatible with the space-time concept, in a sense you can imagine the situations when these unitary dilations are kind of signaling because the excitations, the concept of the particle of the dark sector doesn't fit to the space-time structure at all.
Okay, so for the first question, my point is really different from saying that they are not falsifiable. So they are definitely falsifiable. It's a different point. It's rather, if the opposite happens, that is, they are verified, you can always make a contrived unitary model that has the same predictions. But of course, collapse models can be falsified. It's rather the opposite that is more difficult in a way. That's for the first point. For the second point about Occam's razor and the unitary dilation, collapse models anyway, the one that are currently proposed, violate Lorentz invariance. So they already have a preferred frame. And as a result, the dark sector you introduced also has the same properties. I think the question will be more precisely posed once, and if ever, we have collapse models that are consistent, so that we can really use in the relativistic context. I'm not even saying collapse models that would be relativistic.
Okay, sorry, let me just clarify the point. Sure. I didn't make it more clear enough. So by speaking about the signaling issue, I was just referring to the problem of, logical inconsistencies. For instance, you may have causal loops that are not logically inconsistent, but you may have some theories where it really does, lead to logical inconsistencies. Saying, is it possible to say that in some cases those dilations lead to structures that are logically inconsistent with the concept of space-time? Let me clarify it later.
I see. Frankly, I haven't thought of it. So, yeah, what is true is that I understand your point better. Yeah, empirically, it's certainly the same, because that's all the measurements we could make. But there could be internally something.
So I'm saying,
yeah, I have no idea, I have to say.
okay, okay, thank you.
Maybe that's a good point, because that also brings us right up to the break time. I think that's a good point to make a transition. So people want to take a break, have a break, and the next talk will start at in 20 minutes at 10 to. But this conversation I would love to continue. So I'm going to open a breakout room, and then if people want to keep on discussing this stuff, join the breakout room, we can keep on talking. Okay. So thanks again to the speakers. Yeah, really enjoyed those two talks.